Hello, mariners and maritime enthusiasts, and welcome back to the channel. Today, we're diving deep into a crucial topic that every navigator needs to master: electronic navigation and, more importantly, what happens when our sophisticated systems don't quite agree. We're going to kick off a new series of real-world case studies, starting with a classic but critical scenario: a discrepancy between the radar and the ECDIS. Imagine this. You're on the bridge, navigating through the congested and confined waters of the Singapore Strait. It's a high-traffic area where precision is not just preferred, it's absolutely essential for safety. Your eyes are scanning between your primary navigation tools, the ECDIS, showing your vessel's position as a neat little icon on the electronic chart, and the radar painting a real-time picture of everything around you. On the ECDIS, your ship is perfectly tracking along the planned route. The GPS is feeding it a constant stream of position data, and everything looks textbook perfect. But then, you glance at the radar. You notice something is off. You take a look at a prominent, fixed object on the radar display, let's say a well-defined point of land or a lighthouse. You compare its position on the radar screen to its charted position on the ECDIS. They don't line up. You do a quick check. The radar overlay on your ECDIS, which should perfectly superimpose the radar image onto the chart, is clearly misaligned. The raw radar data shows your vessel is actually about 0.3 nautical miles away from where the GPS-powered ECDIS thinks you are. Now, 0.3 nautical miles might not sound like a huge distance out in the open ocean, but in the Singapore Strait, it's a massive, potentially catastrophic difference. It's the difference between being safely in the channel and being dangerously close to another vessel or a navigational hazard. So, what's going on? Is the radar wrong? Is the ECDIS malfunctioning? This is a moment where a navigator's fundamental skills are put to the test. The immediate reaction might be to trust the modern, smarter system, the ECDIS, with its GPS input. After all, GPS is supposed to be incredibly accurate, right? But the seasoned mariner knows better. You never, ever rely on a single source of information. This is the core principle of cross-checking, or what we call establishing a position of doubt. The bridge team in our case study did exactly the right thing. They didn't panic, and they didn't blindly trust one system over the other. They initiated an investigation. The first and most logical step was to question the integrity of the GPS signal that the ECDIS was relying on. GPS is fantastic, but it's not infallible. Signals can be degraded, there can be atmospheric interference, or, as it turned out in this case, the problem can be much closer to home. Upon investigation, the crew discovered the root cause of the discrepancy. It wasn't a satellite issue or a complex software glitch. It was something much more mundane, yet just as dangerous. Recent maintenance work had been carried out on the ship's mast, and during this work, the primary GPS antenna had been accidentally shifted. It was physically moved from its original, surveyed position. Think about what that means. The ECDIS system was configured to believe the GPS antenna was at a specific point on the vessel. It uses this known position to calculate and display the ship's location on the chart. But with the antenna physically moved, all the data it was receiving was now based on a false reference point. The system was performing its calculations perfectly, but it was working with bad initial data. Garbage in, garbage out. The entire electronic plot was offset by the exact distance the antenna had been moved. This highlights a critical vulnerability in our reliance on GPS. The system itself might be working fine, but if the physical installation, the antenna's location, is compromised, the output will be dangerously inaccurate. So, how did the crew resolve this on the fly, in the middle of one of the world's busiest shipping lanes? They reverted to fundamental, time-honored navigation techniques. They used the radar not just as a collision avoidance tool, but as a primary position fixing instrument. The officer on watch performed a manual position fix. He took bearings and ranges from several fixed, charted objects visible on the radar, things like buoys, headlands, and lighthouses. Using these manual radar fixes, he plotted the ship's true position directly onto the chart. He did this not just once, but repeatedly, creating a series of manual plots. This created a new, manually plotted track line, and guess what? This new track line, based on direct observation from the radar, confirmed that the vessel was indeed 0.3 nautical miles off the GPS-derived tracks shown on the ECDIS. The radar was telling the truth. The GPS position was in error. With the ship's true position now confirmed, the navigator could make the necessary course corrections to bring the vessel back onto the correct, safe track. They were able to continue the passage safely, but they did so by actively navigating, not just monitoring an automated system. They placed a note of caution on the ECDIS display, warning all watch officers of the GPS offset and instructing them to rely on manual radar position fixing until the antenna issue could be permanently resolved. So, what are the key takeaways from this real-world incident? First and foremost, never become complacent. Technology is a powerful aid, but it's not a substitute for good seamanship. The term ECDIS-assisted grounding exists for a reason. It happens when crews place blind faith in the electronic chart without cross-referencing with other available means. Second, always cross-check your position. Use all the tools at your disposal. Radar, visual bearings, depth soundings, even celestial navigation if you can. If you see a discrepancy between any two sources, you must assume your position is in doubt until you can prove otherwise. The radar is your primary tool for collision avoidance, but it's also an incredibly powerful position-fixing tool. Practice using it for that purpose regularly. Third, understand the limitations and potential failure points of your equipment. In this case, it was the physical location of the GPS antenna. Know your systems, read the manuals. Understand how they are set up and what can affect their accuracy. After any maintenance near navigation equipment, it should be standard procedure to verify the performance and calibration of all affected systems. And finally, this case is a powerful reminder of the enduring value of traditional navigation skills. The ability to take a 3-point fix, to plot a running fix, and to assess a situation using raw radar data are not obsolete skills. They are essential safety nets that can and will save you when technology lets you down. This scenario in the Singapore Strait could have ended very differently. An offset of 0.3 miles in those waters could easily lead to a collision or a grounding. It was the crew's vigilance, their healthy skepticism of the automated position, and their proficient use of the radar for position fixing that turned a potentially disastrous situation into a valuable learning experience. Remember, the goal is not to distrust our technology, but to use it wisely and critically. Always maintain situational awareness, and never forget the fundamentals of navigation that have kept mariners safe for centuries. That's all for this case study. I hope you found it insightful. What would you have done in this situation? Let me know your thoughts in the comments below. We can all learn from each other's experiences. If you found this video helpful, please give it a thumbs up, subscribe to the channel, and hit that notification bell so you don't miss our next case study. Until next time, stay safe and fair winds.